All right, welcome to the deep dive where we do exactly that. We go deep, take a whole bunch of interesting stuff and pull out what you actually need to know. Today's deep dive, we're going to be focusing on Hermann Minkowski, a really, really big name in both mathematics and physics from back in the early 1900s. And lucky for us, we have an expert here to walk us through all this, based on the essay by Jörg Schneeppert called Hermann Minkowski, Begründer der Raumzeittheorie.
Yeah, what's really fascinating about Minkowski, even now, is this incredible ability he had to see these deep, deep connections between the really abstract world of mathematics and the kind of tangible workings of the physical world.
Yeah.
I mean, it really allowed him to make these intellectual leaps, these insights, and they just had ripple effects like these shock waves across so many scientific fields.
Yeah, absolutely. I mean, the one that really pops out, at least for me, is his introduction to the four-dimensional space-time, right? And this wasn't just a little tweak to what was already there. I mean, this absolutely transformed the way we understand relativity, and as we're going to get into, it laid some surprising groundwork for quantum physics. Like, who knew?
Exactly. It's often Einstein who gets all the credit. And rightfully so. But Minkowski's contributions were, without a doubt, truly foundational.
Yeah.
Schneeppert's essay does a fantastic job of, really driving home just how broadly Minkowski was thinking. It's everywhere, from pure geometry to, the practical applications we're seeing today in quantum information science, right? It's wild how his ideas continue to be relevant, especially in a field as crazy fast-moving as quantum science and technology.
Okay, so let's get into the meat of it here. Minkowski's foundational contributions, what does he actually do? Schneeppert makes it super clear in his essay that his impact wasn't just on one side, like just math or just physics. I mean, he was a major player in both, which is kind of amazing.
Absolutely. On the mathematics side, he really left his mark with the development of the geometry of numbers.
Okay, so what is that? Geometry of numbers. It sounds kind of weird.
It is, kind of. But what he did was link these two seemingly totally separate areas, right?
Yeah.
You got algebraic number theory, which is all about the properties of numbers, and then you got geometry, which is all about shapes and spaces.
Okay.
So he took these geometric methods and used them to tackle really tricky problems in number theory. He came up with key insights into something called Diophantine equations, which, and this is the interesting part, are equations where you're only looking for solutions that are whole numbers, not fractions, not decimals, just whole numbers.
Okay.
And his work, believe it or not, kind of set the stage for how we do a lot of mathematical analysis today.
So you're telling me he's using shapes to solve number problems. That's the kind of unexpected connection that, makes this deep dive so fascinating.
Exactly.
And then, of course, on the physics side, we have his revolutionary space-time concept. Can we unpack that a bit more?
Yeah, for sure. So the really mind-bending part here, and this is what you really got to wrap your head around, is that Minkowski proposed that we should think about the three spatial dimensions we experience every day, up, down, left, right, forward, backward, and time, not as separate things, but as one unified four-dimensional fabric.
Okay, a four-dimensional.
Yeah, it was a complete shift in perspective.
Yeah.
And it gave this super clean and really elegant mathematical way to describe Einstein's special relativity.
Yeah.
There's this visual tool, the Minkowski diagram, that came out of this. And it really helps you see this interconnectedness of space and time.
Oh, I think I've seen those diagrams. The ones with all the grid with lines going every which way, and they represent space and time.
Right.
Yeah, it definitely makes some of those really abstract ideas a little bit easier to grasp, at least for me.
Yeah, exactly. Makes it more concrete, more tangible.
Schneeppert really hammers home this point, that Minkowski built this bridge between mathematical and physical thinking.
It was a huge deal. And the craziest part, that connection actually had a huge impact on the development of quantum mechanics. Now, we have to be clear, Minkowski wasn't directly involved in the early days of quantum theory. But his ideas, particularly the space-time framework, became absolutely crucial for breakthroughs that came later, like relativistic quantum field theory. Even today, it plays a role in the search for that elusive theory that ties together gravity and quantum mechanics, what we call quantum gravity.
Right. Okay, so Schneeppert's essay really zones in on this impact on the quantum world. What is he trying to get across to us, to the listeners?
So Schneeppert's main objective is to really showcase Hermann Minkowski's specific role and the lasting effect of his work on the development of quantum science and technology as we know it today.
Okay.
And this is important. He wasn't one of the founding fathers of quantum mechanics, like the big names. But his work, both in math and physics, provided the building blocks, the essential foundation for everything that came after.
Okay, so he's kind of setting the stage, laying the groundwork.
Okay.
And Schneeppet poses some key questions, right, that we're going to be tackling in this deep dive.
Yeah, he frames the whole essay around three big questions. First, how did Minkowski's space-time concept actually shape our understanding of quantum physics?
Okay.
Second, which of his specific mathematical tools and methods did scientists later build upon in quantum science?
Okay.
And third, and this was the most intriguing, how relevant are his ideas to those cutting-edge technologies we're seeing today, like quantum computers and quantum networks?
Right. Like, does this stuff even matter in the practical world?
It's a great question, and Schneeppet argues that by exploring these, we'll see that Minkowski's contributions go way beyond their historical significance. They're not just part of the story, they're actively shaping the field.
Yeah, I'm with you on that. Okay, so to really get this, Schneeppet takes us back to Minkowski's life, and his story starts where?
Well, he was born in Lithuania in 1864 in a place called Aleksotas, which was then a suburb of Kaunas.
Okay, Lithuania.
His family was Jewish, and they put a very high value on education and intellectual pursuits. Even from a young age, it was clear that Minkowski had a real gift for mathematics. His teachers saw it right away.
So natural talent, but also a nurturing environment.
Definitely. And the family later moved to Königsberg, which was this buzzing hub of intellectual life in the 19th century. I mean, this was the home of thinkers like Immanuel Kant.
Right, so he's surrounded by these giants of thought.
Exactly. This environment undoubtedly had a huge influence on Minkowski, fostering his passion for challenging mathematical problems.
And he goes on to study at the Albertus University, Königsberg. What happens there?
So he enrolls at the university when he's just 15 years old.
15, wow.
Yeah, super bright kid. He starts off focusing on number theory, but his brilliance in mathematics, particularly in this area called the geometry of numbers, becomes really obvious really fast.
Geometry of numbers again?
Yeah, it keeps popping up.
Oh, it's coming back.
And here's the kicker. In 1883, while he's still a student, he wins this incredibly prestigious award, the Prix Bourdon, from the French Academy of Sciences.
Wow, the French Academy.
Yeah, for his work on quadratic forms. This is a huge deal for someone so young.
I mean, that must have been a huge confidence boost. Like, okay, I'm on the right track here. And then he moves on to Göttingen, which was, at the time, another major center for mathematics and physics.
Yeah, Göttingen was like the place to be for math and physics at that time.
Right.
It was there that he got to interact with and learn from some of the biggest names in the field, people like Felix Klein, and, importantly, his close friend David Hilbert, who had a huge influence on his intellectual development.
So he's surrounded by geniuses.
Yeah, pretty much.
And it sounds like his interests were always right at that intersection of math and physics, even early on.
Yeah, from the start, Minkowski had this knack for connecting these seemingly abstract mathematical structures with actual physical concepts. It's amazing, really. And while he was initially focused on the geometry of numbers, he was also drawn to physics, especially areas like electrodynamics and later on, relativity. This kind of cross-disciplinary thinking, this ability to see connections across fields, became a defining characteristic of his whole career.
It's like he had this wide-angle lens that let him see the bigger picture that most people miss.
Yeah, exactly. He wasn't just focused on one narrow area. He could see the connections, the threads running through everything.
Okay, so from this impressive start, he goes on to hold professorships at some big-name universities.
Right, so after he finishes his doctorate, he goes to Bonn. That's where he really dug deep into number theory and the geometry of numbers. Then, in 1894, he moves to the University of Göttingen.
Back to Göttingen.
Yeah, and there he's a professor, and he's working closely with Felix Klein, and especially with his lifelong buddy, David Hilbert.
And Schneeppet mentions how influential he was in applied mathematics during his time in Göttingen.
Yeah, his impact went way beyond just pure mathematics.
Right, he was making stuff happen in the real world.
Exactly. So then, in 1902, he goes to ETH Zurich as a professor.
ETH Zurich.
That's where he really ramped up his research and started thinking more broadly about physics. And being at ETH also brought him into contact with bright young minds like Albert Einstein.
Einstein.
Yeah, this connection was super important later on.
Okay, so he's collaborating with some of the biggest names in both math and physics. These got to be some pretty productive partnerships.
Yeah, incredibly productive. With David Hilbert, they worked on a huge range of problems, from pure math to more physics-related stuff, especially in analysis and number theory. You can really see Hilbert's influence on Minkowski's later work, when he was diving deep into geometry and physics.
And then there's Einstein.
Right. At first, Minkowski was actually kind of skeptical of Einstein's special relativity. Like, come on, really?
That's kind of funny, right? Two geniuses, and one is like, I don't know about this.
But he quickly realized just how profound it was, how game-changing. And that's when he developed the four-dimensional space-time concept.
The foundation for Einstein's theory.
Exactly. The mathematical bedrock. Now, even though they had different approaches to thinking about physics, they had a huge respect for each other's intellect. It was this mutual admiration society.
Mutual respect, but still challenging each other, pushing each other further.
Exactly. That's how the best science gets done.
Yeah, iron sharpens iron. It sounds like this environment, these collaborations, they were key for Minkowski to really develop those groundbreaking ideas.
Absolutely. They were a catalyst, pushing him to think differently and make those connections between pure math and the physics that underlies the universe.
Okay, let's get to the heart of the matter here. The revolution of space-time. Schneppat spends a good chunk of the essay on this, and for good reason.
Rightly so. This is where Minkowski's impact on physics really shines through.
Okay, so 1908, he introduces this concept of four-dimensional space-time.
And everything changes.
So Schneppat actually quotes Minkowski, right? He says, from now on, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality.
Powerful stuff.
Yeah, it really drives home how radical this idea was.
It's a complete paradigm shift. We're no longer thinking about space and time as separate entities. They're fundamentally intertwined.
Okay, so how does this change things practically?
Before Minkowski, physicists saw space and time as these separate stages where events happened.
Right.
Like a play on a stage, right? But Minkowski shows that space and time are actually woven together, part of the same geometric structure, a four-dimensional tapestry.
Okay, so what does this actually look like mathematically?
So the math behind Minkowski space-time is this thing called a four-dimensional metric. And the equation for it is sobi word paxs plus y plus sobi hat, where x, y, and z are your spatial coordinates. This time includes the speed of light.
Okay, so we got space and time and the speed of light all mixed together in this one equation.
Exactly, and that's what we call the space-time interval between two events.
All right, so this interval, it's like a measure of the distance between events in space-time.
Yeah, but not just distance in the usual sense. It accounts for both the spatial separation and the time difference between events.
And you said there's something special about the negative sign in front of the time component, right?
Yeah, that's what really sets time apart from the spatial dimensions in this model. It means that time isn't just another direction like up or down. It's woven into the fabric of space in this unique way.
So this mathematical framework, it has some pretty big implications for how we understand the physical world, right?
Oh, absolutely. It leads directly to the relativity of space and time.
Relativity.
Yeah, those things we think of as absolutes, like whether two events happen at the same time, the length of an object, even the flow of time itself, all become relative to the observer's motion.
That's wild.
It is. It means there's no universal clock ticking away for everyone. Time passes differently depending on how fast you're moving relative to someone else.
So my time is different from your time.
Exactly. And that difference becomes more pronounced the closer you get to the speed of light.
That's mind-boggling.
It is, but it's all backed up by the math. And it has real, measurable consequences.
Okay, so this brings us back to Einstein's special relativity. How does all this fit together?
So Einstein laid out the core principles of relativity back in 1905. The constant speed of light and the idea that the laws of physics are the same for all observers moving at constant speed. But it was Minkowski who came along and said, hey, here's the perfect mathematical structure to express all this.
You gave it a language.
Exactly. And that structure, it beautifully explains some of the really weird predictions of special relativity, like time dilation and length contraction. It made it all click.
Okay, I'm starting to get the picture here. Schneppat also talks about how this led to the unification of mechanics and electrodynamics.
Yeah, this is another huge contribution. Before Minkowski, we had separate theories for how things move and how electricity and magnetism work. But with his four-dimensional framework, Maxwell's equations, which describe electromagnetism, could be written in this really elegant and compact way, right there in the language of spacetime.
So it brought them together.
Exactly. And this was a big deal for the later development of relativistic quantum mechanics and quantum field theory.
It's amazing how these seemingly disparate things turn out to be so interconnected. All right, let's shift gears a little and talk about how all this space-time stuff influenced quantum mechanics. We know the original Schrödinger equation was just three-dimensional, right?
That's right. The Schrödinger equation, which is the foundation of non-relativistic quantum mechanics, treats space and time in this very lopsided way. It's all about how a quantum system changes over time, but it's stuck in our familiar three spatial dimensions.
Okay.
But then physicists started to think, okay, what happens when these quantum systems are moving really, really fast, like close to the speed of light? How do we describe that?
That's when you need relativity.
Exactly. And that's where Minkowski's spacetime came to the rescue.
And this leads to the development of the Dirac equation.
You got it. The Dirac equation, developed by Paul Dirac, takes the Schrödinger equation and says, all right, let's make this relativistic. And to do that, he uses Minkowski's spacetime concept. He introduces these things called Lorentz invariant operators, represented by these matrices called gamma matrices, which basically ensure that the equation respects the principles of relativity.
So it's like upgrading the Schrödinger equation to be compatible with Einstein's world.
Yeah, exactly. And the Dirac equation describes particles with spin, like electrons. It's a cornerstone of relativistic quantum mechanics.
Wow. So Minkowski's ideas are right there at the heart of how we understand these fundamental particles. And Schneeppert also highlights the importance of his space-time concept in relativistic quantum field theory.
Oh yeah, absolutely essential. Quantum field theory, or QFT, the framework we use to describe the most fundamental forces and particles in the universe. It's all about fields, like the electromagnetic field, or the Higgs field, that permeate space-time. And these fields, they're described using Minkowski's four-dimensional language.
So it's like the language of the universe?
Well, in a way, yeah. And the really cool thing is, you can write the equations for these fields in a way that doesn't change no matter how fast you're moving. That's what we call Lorentz invariance. And it's a direct consequence of Minkowski's work.
Okay, so it's not just about space and time anymore. It's about how we describe the very fabric of reality.
Exactly.
And Schneeppert goes even further, right? He talks about how this framework helps us understand some of the really weird, counterintuitive stuff in quantum field theory.
Yeah, things like virtual particles, which are these particles that pop in and out of existence, and renormalization, which is this crazy mathematical technique we use to deal with infinities that pop up in our calculations.
Infinities.
Yeah, quantum field theory gets a little wild. I bet.
But the key point is, Minkowski's spacetime provides the foundation for all this. It allows us to talk about causality, which means that an effect can't happen before its cause, even in the quantum world.
So it keeps things from getting totally out of control, even when things are super weird.
Exactly.
And then Schneeppert brings up this even more mind-bending area, quantum gravity.
Yeah, the holy grail of modern physics.
Right. So we know that quantum gravity is all about trying to unify quantum mechanics with Einstein's general relativity, which describes gravity as a curvature of spacetime. And this is a big, big problem.
A huge problem.
And Minkowski's spacetime, it's flat, right, not curved. So how does that even work?
So while Minkowski's model doesn't directly account for the curvature of spacetime described by general relativity, it's still incredibly useful for thinking about quantum gravity.
In approaches like loop quantum gravity and string theory, which try to describe spacetime at the most fundamental level, Minkowski's work serves as a kind of starting point or reference frame. It helps us wrap our heads around how space and time might behave at these incredibly small scales, even if we think it's made of discrete units.
So it's a guidepost, even if it's not the whole picture.
Exactly. And even the concept of the light cone, which defines the limits of cause and effect in spacetime, is really useful for ensuring that causality is preserved in these more exotic models of spacetime.
Right. Cause and effect still have to hold.
Absolutely. So even though Minkowski wasn't working on quantum gravity directly, his influence is felt in this incredibly complex field.
Okay, let's move on to the more mathematical side of things. Schneeppert dedicates a section to the tools and methods that Minkowski developed and how they've been used in quantum science.
Right, because beyond his revolutionary ideas about spacetime, Minkowski also made huge contributions to applied mathematics. His development of the geometry of numbers is a prime example.
All right, geometry of numbers. We got to talk about this. What is it, and how does it connect to quantum mechanics?
So imagine you're trying to solve problems about numbers.
Okay.
Instead of just using equations, Minkowski said, let's look at this geometrically. So he took this idea of lattices, which are these repeating patterns of points in space, like a grid, and convex bodies, which are shapes that are kind of rounded, no inward dents.
Oh, okay, I'm picturing it.
And his famous theorem in this area It gives us a way to figure out when one of these convex bodies must contain a point from the lattice. It's a way of connecting shapes and numbers.
All right, but how does this translate to the real world, to something like quantum mechanics?
Well, it turns out that this stuff has applications in the theory of lattice systems, which are really important in condensed matter physics. This is the study of materials. Think about crystals, how their atoms are arranged in these repeating patterns. We can model that using the geometry of numbers.
So it's like we're using geometry to understand the structure of matter.
Exactly. And that structure, it dictates how electrons behave in these materials, what their energy levels are.
Okay, that's pretty cool. Schneeppaa also mentions its relevance to quantum information theory, right?
Yeah, quantum information theory is all about qubits, which are the building blocks of quantum computers.
Right.
And it turns out that Minkowski's work kind of laid the groundwork for some of the optimization and encoding techniques we use in quantum information. His geometric approach gives us a way to describe and manipulate these complex spaces where qubits live.
So it's like he gave us the tools to work with these quantum systems.
In a way, yeah. And then there's the connection to Hilbert spaces. These are the mathematical structures that are at the heart of quantum mechanics.
Okay.
So David Hilbert gets the credit for developing them. But Minkowski's work in formalizing geometric concepts definitely contributed to the whole mathematical environment that made Hilbert spaces possible.
Right.
And his work on transformations in spacetime geometry using these things called four vectors was crucial for coming up with mathematical expressions that don't change under Lorentz transformations. These are fundamental to relativistic quantum mechanics and quantum field theory.
So his influence is kind of everywhere, even in the math behind it all. Okay, now we got to talk about the Minkowski diagram. Schneeppaa makes a big deal about it, and for good reason.
The Minkowski diagram is such a powerful visual tool for understanding spacetime. It's basically a graph, but instead of plotting just two spatial dimensions, it plots one spatial dimension and time. So you get this picture of how events are related in spacetime.
Okay.
The really cool part is the light cones. They show all the possible paths light can take from a particular event. And these light cones, they define the boundaries of cause and effect.
So it's like a roadmap for cause and effect in this four-dimensional world.
Exactly. If an event is outside your light cone, it can't possibly influence you, and you can't influence it.
Because nothing can travel faster than light.
Right. So the diagram helps you visualize things like why two observers moving relative to each other might disagree on the order of events. It gets kind of mind-bendy.
Yeah, but the diagram helps make it a little less abstract.
Exactly. And it's particularly useful in quantum mechanics, especially in quantum field theory, because it helps us understand how particles interact, taking into account that nothing can travel faster than light.
Okay, so it's not just a teaching tool, it's actually used in research. Schneeppaa gives some examples, right?
Yeah, it's really useful in quantum cryptography, which is all about secure communication.
Right.
So in methods like quantum key distribution, we use Minkowski diagrams to analyze the timing and spatial relationships between the sender and receiver of quantum information.
Okay.
This helps us ensure that the transmission of qubits, those quantum bits of information, is secure, and that no eavesdropper can intercept the information without being detected.
That's pretty clever, using relativity to secure quantum communication.
It is, and it goes beyond cryptography. In quantum information theory in general, Minkowski diagrams help us understand things like quantum teleportation and entanglement, and show that they don't actually violate the speed limit of the universe.
Okay, so they help keep things consistent with Einstein's world.
Exactly.
It's incredible how Minkowski's ideas, over a century old, are still finding new applications in these cutting-edge fields. Schneeppaa also explores how his work influenced later generations of scientists and how it's being used in quantum informatics.
Yeah, Minkowski's space-time concept was like this seed that was planted, and it grew into something really profound.
A seed that influenced some of the biggest names in 20th century physics.
Right, like Paul Dirac, who we mentioned earlier, who used it to develop the Dirac equation. And then there's Richard Feynman, the guy behind Feynman diagrams.
Those iconic squiggly lines.
Yeah, exactly. So Feynman, he was also heavily influenced by Minkowski's ideas about light cones and causality. And his path, integral formulation of quantum mechanics, which is a whole other deep dive, it's also framed within this Minkowski space-time perspective.
So Minkowski's thinking became part of the DNA of quantum mechanics.
You got it. And his mathematical tools, the way he used four vectors and came up with expressions that don't change under Lorentz transformations, that all became essential to modern quantum physics.
Yeah.
We use it to describe everything from the electromagnetic field to the Higgs field.
Okay, so it's not just about space and time anymore. It's about how we describe reality at the most fundamental level.
Exactly.
And then Schneepat gets into quantum informatics, the world of quantum computers and all that.
Yeah, and it turns out that Minkowski's ideas are having a huge impact there, too.
Right.
You can think of a quantum computer as operating within this space-time structure, where even qubits, the building blocks of quantum information, are subject to the limits of causality.
So even in the quantum world, cause and effect still rule.
Absolutely.
Mm-hmm.
And that has big implications for how we design and build quantum computers.
Mm.
The very way we design quantum circuits, it has to respect the rules of space-time.
Right.
And when we implement those amazing quantum algorithms, like Shor's algorithm for factoring numbers, which is a big deal for cryptography, or Grover's algorithm for searching databases, all that has to happen within the framework of Minkowski's spacetime.
Okay, so it's like he's setting the boundaries, even in this super advanced field.
Yeah, in a way.
Yeah.
And Schneepat mentions how it even applies to quantum parallelism, where a quantum computer can explore many possibilities at once, and quantum error correction, which is crucial for building reliable quantum computers.
Right.
And beyond just quantum computers, Minkowski's ideas are also shaping how we think about quantum networks.
These networks that connect quantum computers together.
Exactly. So when we're transmitting quantum information over long distances, we have to make sure we don't violate the speed limit of the universe.
Right.
And Minkowski's concept of the spacetime interval helps us do that. Quantum cryptography protocols, like BB84, are a great example. They use the properties of light, which is governed by spacetime, to ensure secure communication.
So it's like we're using the very fabric of reality to protect our information.
In a way, yeah. And Schneepat even talks about some really out there ideas like time loops and time entanglement in quantum communication, which are directly inspired by Minkowski's work.
Wow, so he's still pushing the boundaries, even from beyond the grave.
It's pretty amazing.
Okay, now Schneepat also gives us a bit of a reality check, right? He acknowledges that there are some limitations to Minkowski's ideas when we apply them to the quantum world.
Yeah, we got to be honest about that. As powerful as his framework is, it's not a perfect fit for everything. One of the big challenges is trying to reconcile his spacetime concept with gravity.
Right, because Minkowski's spacetime is flat, but Einstein showed us that gravity warps spacetime. It's curved. So how do we reconcile that?
It's a big question, and it's at the heart of the search for a unified theory of quantum gravity. In quantum field theory, which is our best description of the quantum world so far, we usually assume spacetime is flat, like Minkowski's model. But general relativity tells us that spacetime is curved, especially near massive objects.
Okay.
And at really, really small scales, like the Planck scale, where quantum effects of gravity are expected to be significant, Minkowski's smooth, continuous spacetime might not even be the right description. Some theories suggest we need something more discrete, more like a granular structure.
So it's like our current picture breaks down at those extremes.
Yeah, and it's not just about small scales. When you think about extreme events like black holes and the Big Bang, where you have these singularities with infinite densities, the classical concept of space-time just falls apart.
Right, our equations go haywire.
Exactly. And quantum field theory, which is built on Minkowski's space-time, just can't handle that.
Yeah.
So it suggests we need a more fundamental revision of how we think about space-time itself.
Okay, so we're missing something big. And then there's the whole issue of entanglement, right?
Yeah, quantum entanglement, where two particles are linked in this spooky way. Even when they're far apart, it creates this tension with Minkowski's picture of causality.
Right, because entanglement seems to imply instantaneous connections, which would violate the speed limit of light.
Exactly. And Minkowski's model is all about respecting that speed limit. So this raises some really deep questions. Maybe Minkowski's model isn't the whole story, or maybe it's just an approximation that works really well in certain situations.
But not everywhere.
Right.
Okay, so despite these limitations, Schneepat makes it clear that Minkowski's work is still incredibly relevant today.
Oh, absolutely. His ideas are everywhere in cutting-edge research, from quantum communication to quantum sensor technology.
So it's not just theoretical, it's practical too.
Exactly. Schneepat points out how the principle of causality, which Minkowski's work really clarified, is crucial for developing secure quantum cryptography protocols. The fact that information can't travel faster than light, as defined by those light cones, is what makes quantum key distribution so secure.
So even though there might be weird quantum stuff going on, like entanglement, we can still rely on those fundamental limits of space-time to protect our information.
Exactly. And he gives the example of long-distance quantum key exchange, where we use Minkowski's concept of the space-time interval to ensure that the transmission is secure and can't be eavesdropped on.
Okay, that's pretty cool. And what about quantum sensors?
So quantum sensors are all about using quantum effects to make incredibly sensitive measurements.
Right, like measuring gravity waves.
Exactly. And those sensors rely on our understanding of space-time. Minkowski's framework gives us the language and the tools to model how these quantum systems interact with their environment, how they're influenced by gravity, for example.
So even though Minkowski wasn't thinking about quantum sensors,